Hello everyone. Today, I want to bring you news of a really cool, recent discovery on Mars. On June 8th, so just 6 days ago at the time of this recording, two studies were published in the journal Science that presented data about organic molecules found on Mars. These findings are really exciting because they're tantalizing clues into Mars's past and the possibility of ancient Martian life. As time goes on, and more of these discoveries are made, we build an increasingly sophisticated picture of potential life on the red planet. The discoveries that are detailed in these two most recent papers are giant brushstrokes that greatly enlarge this picture that we're painting of life on Mars. Now, I've talked about life on Mars a lot. I recently posted a really in-depth episode about potential life on Mars. And one of the things that I talked about the most frequently is how the surface of Mars is completely irradiated. The atmosphere is thin and weak, and the core is geologically dead, so there's no magnetosphere. In short, there's nothing to protect the surface from solar radiation, and ultraviolet light is able to saturate and sterilize the surface soil. This has long been thought to imply that no life exists in the upper few meters of the crust, as soft organic cells would eventually be destroyed by a perpetual influx of UV radiation. Now, thanks to the first study, this standard line of thinking has been somewhat invalidated. The Curiosity rover has been on Mars for close to 6 years now. It first landed in the Aeolus Palus, a large, low-altitude plain lying in the northern regions of the Gale crater. Gale crater is a very large crater, and it's believed to be the remains of an ancient lake bed, as there's ample evidence surrounding the crater of outflow channels. The rock has very clearly been eroded by fluid, most likely liquid water, that once fed into ancient Martian rivers. Because of this probable background, Gale crater has been determined to be a potential hotspot of biomolecules, and maybe even lingering organic activity. Most recently, Curiosity visited the Pahrump foothills, which exist in the central region of Gale crater, at the base of Aeolus Mons, or Mount Sharp. Here, in the Pahrump foothills, NASA is having Curiosity examine sedimentary rocks that were most likely formed in the presence of liquid water. These rocks, called lacustrine mudstones, likely formed more than 3 billion years ago, as they represent material from Mars's youth. By sampling the rocks and baking the sample to produce identifiable gaseous byproducts, Curiosity found preserved organic molecules, like thiophenic, aromatic, and aliphatic compounds. This suggests that these lacustrine mudstones are very similar to the organic-rich sedimentary rock that we can find all over Earth. The researchers say in their abstract that, quote, thiophenes were also observed by gas chromatography, mass spectrometry. Their presence suggests that sulfurization aided organic matter preservation. At least 50 nanomoles of organic carbon persists, probably as macromolecules containing 5% carbon as organic sulfur molecules, unquote. The concentration of this organic carbon is about 10 parts per million, which is comparable to the amount of organic carbon that's found in Martian meteorites. Now, without getting too far off subject, I've made an episode about panspermia, where I discussed the probability that some ejected Martian rocks, carrying either biomolecules or even primitive cells, were able to make it to Earth and seed this planet with life. Discoveries like the one that Curiosity made here correlate with this panspermia hypothesis, and they support its viability as a realistically plausible phenomenon. Okay, so why is all of this so cool? Besides the obvious, the origin of life, right? But it's cool because these rocks, with the preserved organic compounds, were found basically right there on the surface. Even though the organic molecules were embedded within this sedimentary rock, that rock was right there, eating the full brunt of UV radiation from the sun. If organic compounds can persist in sedimentary rock just a few centimeters from the irradiated atmosphere, then the implication here is really incredible. It's possible then that, theoretically, every sedimentary rock on the surface of Mars could host these biomolecules, assuming they were generated around the same time period, and with roughly similar exposures to sulfur and liquid water. If the surface of Mars is this much more friendly to life than we expected, then that greatly improves the chances that there might still be some kind of living cells, some living extremophiles that are just clinging to life, billions of years after the larger Martian ecology has died and disappeared. Maybe there's not even cells left, but maybe there is some kind of weird last gasp of the superreaction of Martian life. I don't know what we might find, but it's really exciting to think about. Now, with all of this being said, the second study is also really exciting. All of this is super fun, isn't it? I mean, I can't get enough of this. I think it's the coolest stuff in the world. I mean, it's the coolest stuff in the solar system, at least. But okay, so over the course of 3 Martian years, which is a little more than 5 Earth years, Curiosity sampled and recorded the concentration of methane in the thin, cold Martian atmosphere. Methane is another organic molecule. It's composed of a carbon atom bound to 4 hydrogen atoms, which are arranged in a tetrahedral shape. Methane can be generated through both biological and geological processes, so at this time NASA can't rule out either option as the source of this methane. But there is a very interesting detail. It's interesting because Curiosity has been taking these samples for so long that NASA has been able to witness seasonal changes in the concentration of methane in the atmosphere in places all around Gale Crater. Every summer, when the temperature rises and things become a little more tolerable from an earthly perspective, the concentration of methane in the atmosphere rises to almost 3 times its winter concentration. Furthermore, the researchers say, and I quote, "The large seasonal variation in the background and occurrences of higher temporary spikes, like 7 ppbv, are consistent with small localized sources of methane from Martian surface or subsurface reservoirs," unquote. So what does a seasonal, cyclical pattern in the concentration of atmospheric methane imply about how that methane is generated? Well, there's thermogenic methane, which is methane that's been formed through the breakup and the decay of organic material under high temperatures and pressures. However, this thermogenic methane is largely produced by inorganic crystalline bedrock, which is some distance below the surface. Pressure is also an important variable here, where higher pressures greatly encourage the formation of this thermogenic methane. The problems that I see with this particular explanation are that the summer months on Mars are really only relatively warm compared to other months on Mars. By Earth standards, Martian summers are pretty cold. I mean, most of the planet is still pretty cold, even in the summer. The only comfortable summer temps are found near the equator, in the height of summer, in the middle of the day. So even though it's relatively warm for Mars, I'm not sure if this background heat is enough to encourage thermogenesis of methane on any significant scale. And then you also have the pressure, which isn't high. The Martian atmosphere has a really low pressure, and these rocks are just on the surface. They're not bedrock that's deep underground, being crushed by, who knows how many tons of rock above them. So the physical pressure on these organic molecule-containing rocks, it's pretty light. There's another geological process called serpentinization, wherein an iron-containing compound like ferrous hydroxide, phthalate, or forsterite will react with water to produce a mineral called serpentine. Byproducts are also produced in these reactions, like magnetite, magnesite, silica, and hydrogen gas, among others. When these serpentinization reactions take place in the presence of carbon dioxide, they can also produce methane. This geological process, in my opinion, is a lot more likely of an explanation of the cyclical changes in Martian methane concentration. It would make a lot of sense if the warmer summer temperatures stimulated more serpentinization reactions, which, in the presence of Mars's CO2-rich atmosphere, I think it's above 90% CO2 or something like that, This would create more methane. The CO2 is there. Magnetite is also a product of this particular reaction. So further sampling on Mars that finds excess magnetite or increased magnetite deposition during the summer would strongly suggest that this methane is generated through this abiotic serpentinization process. It would be purely geological. And this is the BioLogic podcast, so in my opinion, that would be kinda lame. I would be really excited by a biological explanation. Now, on the other hand, we do have that biological explanation, which NASA can't rule out yet. We have methanogenesis. This is a biological process wherein various microbes consume carbon dioxide and hydrogen, and they produce water and methane. If this is what's happening, then what we're seeing on Mars is the summer months bringing heat that stimulates these microbes, and it either feeds them energy directly, like they might be thermophilic, or it provides just an ambient chemical energy that's necessary for other kinds of complex organic reactions. In the winter months, this methane production drops, as the cooler temperatures would theoretically suppress this microbial metabolic activity. Recall that one of the studies explained how this methane was being produced by small, localized sources. This is what we would expect if we hypothesize that there are small, isolated microbial communities or some kind of biological analog that's living inside of sedimentary Martian rock. Now, this is obviously the much more exciting possibility, as active methanogenesis on Mars would directly imply the presence of life, of Martian life, that represents the last living descendants of a biosphere that existed on the red planet billions of years ago. If this is what future data suggests, and we look deeper and eventually find living cells undergoing seasonal changes and seasonal cycles of methanogenesis, well then, we've just found alien life. We'll have to rewrite our notions of the universe, taking into consideration the fact that life appears to be able to linger in seemingly inhospitable places for far longer periods of time than we could have expected. Now, I could go on about how cool it would be to find living Martian cells, or a Martian analog, and what all of the awesome implications of this would be, from genetics to astrobiology to religion. And believe me, I really want to. I really just want to dive into this subject as thoroughly as I can. But I won't, because I don't want to get carried away, and I don't want to give a false impression of what these discoveries mean. Like I said at the beginning of this segment, these studies have not found life. They have not found direct evidence of life. Jen Eigenbrode is the lead author of one of these two papers, and she said, and I quote, "Curiosity has not determined the source of the organic molecules. Whether it holds a record of ancient life, was food for life, or has existed in the absence of life, organic matter in Martian materials holds chemical clues to planetary conditions and processes." Unquote. What these studies have found are really tantalizing nuggets of data that show how Mars is quite likely much more hospitable than we think. These discoveries are like suggestive clues, hints, or breadcrumbs leading us on a trail to find life. Thomas Zurbecken is an associate administrator for the Science Mission Directorate at NASA HQ, and he said, and I quote, "With these new findings, Mars is telling us to stay the course and keep searching for evidence of life. I'm confident that our ongoing and planned missions will unlock even more breathtaking discoveries on the red planet." Unquote. Jen Eigenbrode could also be quoted as saying, "The Martian surface is exposed to radiation from space. Both radiation and harsh chemicals break down organic matter. Finding ancient organic molecules in the top 5 centimeters of rock that was deposited when Mars may have been habitable bodes well for us to learn the story of organic molecules on Mars with future missions that will drill deeper." Unquote. So there you have it. While Curiosity hasn't found proof of life directly, it has found remarkable evidence of organic molecules preserved on the surface for billions of years. and it's found evidence of seasonal changes in methane concentration, coming out from isolated locations within Gale Crater. All of this is really highly suggestive of life. It's incredibly exciting, and I can't wait to see what else the Curiosity rover mission finds, and the discoveries that will be made by future missions.